Good afternoon, dear students. Today we start the 7th lecture in this series on research methodology. And the topic for today's lecture will be statistics and error analysis. As I show you again the steps of the research process. So we have discussed how to do the experimentation, what are the precautions, what are the aspects that you have to take care while recording your data. And then one of the most important aspects of this arriving at some meaningful results is the statistical analysis of your data. Because many a times you may be recording some information, but it may not be significant. So this like signal to noise ratio is very important in your measurements. And so in today's lecture, we will discuss the statistical aspects of handling the data. And this particular lecture, I have not kept very much details of statistics, considering the heterogeneous nature of the students, right from physics to mathematics to even the simple humanities and biology. So I have taken, a general view of the statistics required for analysis of data of all types. And those who are from the mathematics and physics background, maybe they may find it a little simple. And in case they want to go for more detailed analysis of their data, then they may have to go for the in-depth study separately. So this is for general science researchers who may require to use the statistical analysis of their data to arrive at some significant results. So in particular, in many cases, we need to arrive at the sample size. That is one of the important aspects. Now, when you do a survey, then what should be the sample size? Like even for the efficacy of a medicine, when you say this is this much percentage effective, how those data are arrived at, I'll discuss then on that. So in general, the whole idea about this statistical analysis is to arrive at the true values from the sample values that I will be emphasizing in my presentation. So what is statistics? Statistics is the mathematics of measurements and data. How do we handle the data? You may have a large number of data, but you get some quantities like, for the distributions of statistics, we call moments. Moments of a distribution, the people who are in mathematics and physics, they will know, like the first moment is the mean, second moment is the variance, and so on. But we will talk about in simple terms, in terms of the mean and standard deviation when we are handling the data. Summarizing the huge number of measurements and understanding the significance of the measurements. So we have a large number of data. What do we make out of this data that we had discussed? Then how to deal with the measurement error. So whatever number you have got, how to quote the error on that and what does that error mean? Then how to determine the precision and accuracy of a measurement also comes out of the statistical analysis. And this is for today and tomorrow. Some of this which I am listing here may be discussed in tomorrow's lecture. How to describe distributed quantities. You may have a large set of data falling into different bins. How to describe them and how to determine the sample size for a particular study. Okay, so just to give you a very simple example of distributed quantities, I have taken a simple data like, the height of 20 students in a class in centimeters. So, if one can do a simple experiment, measurement of the heights of the students in the class and just write them down, then how to represent this data? Suppose there are a large number of data, you cannot write all of them in the tabular form. So you devise some mechanisms like frequency distributions. So you can have groups or what you call as the class intervals. So this class interval, we can divide this all of them into in the entire range from minimum to maximum. We can divide into, let us say, 160 to 180, and then divide into class intervals 160, 64, 65, 69, 70, 74, 75, 79, and then see how many data fall in which bin. And this is basically we are getting the frequency distribution of the different class intervals, and you can plot them as a function of the class intervals, which you call as the histogram or the frequency of different class intervals. So this is how instead of in all data you put in the form of bins. So pictorially you can represent your data, but in fact, to be one step ahead, if you don't want to give all the data, you give them certain quantities derived from this distribution, then it becomes very easy to comprehend the whole problem. So there are some quantities called the measures of central tendency. That means which tell us about the center or the averages, what are the values around which the other data will be scattered. So the measures of central tendency like mean, median, mode, and so on. So the mean height of the class students in this class, you can calculate like the mean x bar. You sum all of them over all the number of students and divide by the total number of students. So like here, you get the total heights divided by the number of students and you get the mean value. So this is the mean height of the average height of students in the class in centimeters. So this is what is called as the measures of central tendency. You can also you arrange them in the increasing order and you can find the median, which is the middle value. And the other way is the mode, which is the value having the maximum frequency. So these are the different measures of central tendency. And then there is a measure of dispersion. What is the spread among in the values around the mean? So that is the standard deviation. The standard deviation is sigma, and you calculate it as you take the differences from the deviation from the mean. So xi minus x bar is the deviation, and square them. Why we are squaring? Because the deviations could be plus or minus. So it does. If you just add the deviations, they may cancel out. So you square them, sum over all the data, and then divide by n minus 1. That is called the degree of freedom. So we don't divide by n, but we divide by n minus 1 because this data has been already used to derive one parameter of this distribution, that is the mean. So there is 1 degree of freedom less. So this is how you calculate the standard deviation from the sample of your interest. So this you can represent now that the mean height of the students is 167.9 and the standard deviation is 5.1. We can write 167, the height of the students 167.9 plus minus 5.1, that is called the 1 sigma. And we will discuss more on this sigma concept later on, more details. So this values, whatever observations that you get out of your measurements, it could be discrete variables like in this example, we have the heights of the students, is the numbers or the number of students in the class, number of items. Whenever you are counting the items, you are getting discrete variables. And many of the times when you are doing measurements of lengths, distances, weights, then you don't get them in integer values, that you get in rational numbers, and you can then plot them as a continuous variable. So the observations could be discrete or continuous, and accordingly you may have to use different distributions. Now we will discuss a bit about the probability distributions, which is very important when you are trying to guessing the outcomes of a measurement. So when you do the probability distribution, you have a sample and you are doing some measurements. There are probability of a particular outcome. So the total sample space is nothing but all possible outcomes of a measurement form what you call it the sample space. Then the probability distribution like px, takes a function that takes the value for every point x in the sample space. So you have a sample space, and for every point you have a probability distribution. So distributions could be discrete or continuous. Discrete variables will take these values like integer values x1, x2. And so when you want to write the distribution, order distribution, you have these n measurements where the frequency distribution is like ni times you get xi outcome and so on. So the sum of all the ni's from 1 to m outcomes is v n, and the probability distribution for x value, you can px, will be the probability of a particular observation x is ni by n, how many times that x is coming divided by the total number of observations. And then you can normalize the probability distribution. So now total probability is 1. So I equal to 1 to m, px equal to 1. Just to give an example, like you are flipping a coin, and a coin has two sides, so you get the tail or the head. So the probability of the tail is half, probability of the head is half. So you get P0 is half, P1 is half, and the sum total of the two probability is half plus half equal to 1. So this is a very simple example of a what we call as the binomial distribution, which I will discuss little more in details. So binomial distribution, like when you have two outcomes of a measurement and many observations, many measurements you can write as binomial distribution. Like, when you are flipping a coin, you say what's the probability of getting head and tail. Similarly, if you are, suppose you are having some race and there are many people who are competing, and you take a particular competitor and say what is the probability of that competitor winning. So that probability of that is either he wins or does not win. So you have two options. Similarly, the success of an experiment or the winning of a candidate in an election. So anywhere you can have two options, and then they follow a binomial distribution. The binomial distribution is the most general form of statistical models. Different models we will discuss in this lecture. So if the n is the number of trials, and for each trial we have a success probability p, like I said, coin, how many times head will come, p probability for that. Then the predicted probability of counting exactly x successes we can show in terms of the what we call as the binomial distribution, according to which the probability for x as an outcome is n factorial upon n minus x factorial into x factorial. At n factorial, n into n minus 1 into so on into up to 1. And p is the probability of that particular outcome, and 1 minus p is the like this is the success, this is the failure, and the power of x at n minus x. So now this binomial distribution is defined only for the integer values of n and x, and this binomial distribution is normalized. So you have x equal to 0 to n. If you sum over all probabilities, then you get equal to 1. Like I have given an example of a binomial distribution when you flip a coin 4 times. So when you flip a coin 4 times, you can get either 0, you can get, the outcomes could be, so many heads. So 4 times you may have no head, 1 head, 2 head, 3 head, and 4 heads. So now if you see the probability of getting different observations, you have n plus 1 outcomes, like no head, 1 head, 2 head, 3 head, and 4 heads, and they follow. You can calculate the probability by this formula, and since it is normalized, you see the total is equal to 1. So this is what is the discrete distribution of the probability of different outcomes when a coin is flipped 4 times. So you can calculate the mean of the this distribution. The mean for a distribution, like if this is the probability, so x into px, sum over all values of x, will give you the mean. And in this particular case, for binomial distribution, it happens to be n into p, where n is the number of outcomes and p is the probability of a particular outcome. The variance, the second moment, is the measure of dispersion, sigma square, is again, as I discussed, x minus x bar square into px. So in those who are in the physics and maybe mathematics, they will know these are the expectation values of the first and second moment of the distributions. So the variance can be given for binomial distribution, np 1 minus p. You can also write this as q. If q is the failure and p is the success, then npq also can be written in term for the variance. So you can calculate using the binomial distribution the probability of different outcomes of a measurement. Another useful distribution is the Poisson's distribution. It can be derived from the binomial distribution under certain conditions. Like, when we say NP, the mean for the binomial distribution is NP. When the probability is very small, the probability P is very small and constant, then we say the binomial distribution can be reduced to a form which is the Poisson's distribution. Px equal to Pn to the power x minus e raised to minus Pm upon x factorial. And x bar we can write as Pn. So you can write is for Poisson's distribution also, mean is equal to Np. So you can write Px equal to x bar to the power x e raised to minus x upon x bar x factorial. So it should have been here Pn. So now earlier the binomial distribution has two parameters, n and p, but the Poisson's distribution has only one parameter, that is x bar, because the variance also is equal to x bar. Variance is same as mean for a Poisson's distribution. Again, the Poisson's distribution is normalized like binomial distribution. That means sum of all the probabilities is equal to 1. The mean for a Poisson distribution is NP and the variance sigma square is NP. So you can see here, variance, the standard deviation is equal to square root of mean. So many a times you can make use of this formulation in arriving at the standard deviation. Just to give you an example, let us say now, is the example of Poisson's distribution. You take 1,000 people randomly, and today suppose you have got a gathering, a party in a place, and you want to find out how many of them have their birthday today. So that is the problem. So the probability of somebody's birthday falling today is 1 by 365. And if there are 1,000 people, then the mean value is NP, N into P, that is 1,000 into 1 upon 365, that is 2.75. So on the average, 2.75 persons will have. So you have to round it to the nearest integer. And then standard deviation is root x, so 1.66. So this is how you can use the Poisson's distribution to arrive at to predict about the outcomes of a sample study. And in radioactivity decay, radioactive decay also follows the Poisson's distribution. The probability of decay of an atom is 1 minus e raised to minus lambda t. The e raised to minus lambda t is the survival probability. So the decay probability is 1 minus that. And it is very small and it's constant, assuming that the half-lives. So when you take an ensemble of a radioactive substance, it may have a large number of atoms. Maybe if you take a gram, then you will have very, very large number, 10 power 20, 21, 22 atoms. And the probability of decay of each atom is very, very small. So such a decay, radioactive decay, follows Poisson's distribution. And when you do radioactivity counting in our detector, you get some counts. Again, the detection, so which atoms are decaying, we do not know. So we get some counts, let us say 10 counts, 100 counts, and we want to, and the radioactive sample is decaying. So how do you arrive at the error on that number? So we use the Poisson distribution. So suppose we cannot do repeated measurement of a sample because the sample is decaying. So we get one number, one count, let us say 100 counts. So we take the help of Poisson's distribution. The error on that 100 will be square root of 100 is 10. So when we say one measurement, we get 100 counts plus minus 10. So you have 10% error, 10 out of 100. If you want to improve the error on measurements, you suppose you increase the counting time and you get, let us say 10,000 counts. In 10,000 counts, the error will be square root of 10,000 means 100. So it becomes 1%. So that is how the errors are minimized in the radioactivity measurements. So you have to statistically get good data to reduce the errors. So we make use of this Poisson distribution in reducing the errors in counting data. Then the third distribution is the Gaussian distribution. We also call it the normal distribution. So in binomial distribution, when the probability was too low, much less than 1, then the binomial distribution gets reduced to Poisson's distribution. And in the Poisson's distribution, when the NP value becomes much larger than 10, 20, then the Poisson's distribution tends to a Gaussian distribution. And the Gaussian distribution then can be written in terms of the probability Px 1 by root 2 pi x bar. This it is inside the square root e raised to minus x bar square upon 2x bar. So here, since we are reducing it from the Poisson's distribution, we are taking it that the variance is equal to mean. So it is a normalized distribution. It is characterized by single parameter mean x bar because the variance is equal to x bar. But in the normal Gaussians, it is not always true that all Gaussians have variance equal to x bar. Now this coming to that previous example of 1,000 people and having the birthdays on a particular day, suppose instead of 1,000 people, we take 10,000 people and find how many of them have birthdays on a particular day, then NP will be 10,000 into 1 by 365, 27.4, which is more than 20. And so X bar will be 27.4 and sigma will be root of X bar 5.23. So that is how you can, in fact, when the number of the sample size becomes very high, then the Poisson distribution tends to a Gaussian distribution. So you will see that if you plot this data, the distributions, you will find that the probability distribution function slowly becomes a slowly varying function, and it can be assumed as a continuous function. So that is what is the normal distribution, Gaussian distribution. It can take the continuous values of x. So we will be discussing most of our results in terms of a Gaussian distribution, particularly because we will be handling large number of samples, large samples. So for a continuous random variable x, the normal distribution will be given by Px 1 upon root. This is the standard form of a Gaussian distribution. 1 by root 2 pi sigma square e raised to minus x minus mu square upon 2 sigma square, where the x can take the value from minus infinity to plus infinity if it is a continuous variable. The central concept of statistics is to make use of these mathematical results about probability distributions to estimate the likelihood of observing various results from this data. So we can concentrate on this graph, which is a Gaussian distribution for a continuous variable. I have given two x variables here. So if you plot this as a function of x here, then for the x value taking, so the mean of this Gaussian distribution is mu, and I have put them vertical bars corresponding to mu plus 1 sigma, mu plus 2 sigma, mu plus 3 sigma, and similarly on the other sides. So it is actually called a two-tailed distribution. It can take negative and positive values. Now here, what I have shown here is the area under the graph. So the area encompassed by mu plus minus 1 sigma. So mu minus sigma to mu plus 1 sigma constitutes the area under this graph as 68.3%. Mu plus minus 2 sigma encompasses the area 95.44%. And mu plus minus 3 sigma constitutes 99.74%. So these are in fact called as the confidence intervals. So for example, when you do some measurements and you get a mu and you have the sigma value, so within you can set up the confidence intervals that if your mean of the measurement will lie within this much with this much confidence, within this much with this much confidence, and so on. So this helps us in defining the confidence interval. So higher the value, higher the confidence, higher is the value of this, what we call as the Z. So this Z interval, when I say here 1, 2, 3, you can have a continuous variation of Z, that is called the Z variate of normal distribution. So you can write mu plus minus Z sigma. Instead of 1, 2, 3 sigma, you can say mu plus minus Z sigma. And so you can have a Z as a variable. So Z can be written as x minus mu by sigma. So that is equal to Z. So the Gaussian distribution with one variable can also be written as Pz equal to 1 by root 2 pi e raised to minus z square by 2. And these are the values of Z on the x-axis, Z equal to 0, 1, 2, 3, minus 1, minus 2. So you can have continuous values of Z and the probabilities of different Z values are here. So you have one parameter Z, and for that the distribution is given here. So you can see here that for 95% confidence interval, Z equal to 1.96. So that means it will be somewhere here. And for somewhere here, for 99% confidence, Z will be 2.57. So many a times we tell in terms of 95% confidence, 99% confidence. So we use these values of Z. So this much times the sigma. That is how you have to define the confidence intervals. So now let us discuss about the sample and population. So when we say population, essentially it is the, we can also call it a universe, true value. So that is the mean of the entire population. When we have we want to get information about the entire universe. So we say this is the population. And then since we cannot do the complete study of the complete population, we take a sample from the population and derive the data. So every time it is not possible to do all measurements on the whole population because the population size may be very, very small. So that is why we go for sampling. Sampling is required because it saves the time and money. See, whenever you are doing an experiment in the laboratory, you are always doing a measurement on the sample. If you are doing a survey, you are doing a sample survey. You cannot measurement of all the people, or even any kind of measurement and testing you do, efficacy of a medicine, or any survey you do. You don't do measurement of all the. You don't take opinion of all the people, but you take a representative sample. Based on that representative sample, you predict the behavior of the entire population. That is what is meaning of sample and population. So sampling saves time and money. And if the population is infinite, it is the only way of doing measurements. It remains the only choice when a test involves destruction of the item under. Many times, let us say to analyze a sample, you have to destroy the sample. So you cannot destroy the all the samples. So you have to take a few samples and do the analysis. And it helps in obtaining some characteristics of the population. What is population? Population is the total items in the field of inquiry or study. It may be finite. For example, you have the population of a city or workers in a factory, So there is a finite population, though it is also very, very large, but it could be, or it could be infinite, like the stars in the sky or a jumps in the body of a person. You cannot count them. So the number of items in a population we will call as capital N henceforth. So mind you remember it that whenever we are saying capital N, it is the number of items in the population. Now, when you do a sample analysis, from that we get some parameters. So for the population, they are called parameter, and for the sample, they are called statistics. So the characteristic of a sample, like the sample mean or the median or mode or variance, they are called statistics. Whereas the characteristics of the population, like mean, population variance, or standard deviation, are called as parameters. So that is the terminology we use when we differentiate between the moments of a sample distribution and the population distribution. The moments of the population distribution are called parameters, and the moments of the sample distribution are called statistics. So the objective of this sampling is to obtain the estimate of a parameter from a statistics. That is what is the whole thing about in this particular case. Now, so when we are doing sampling, so we do one sample and then we have to do multiple samples. So we will discuss later on that how many samples are required to arrive at a meaningful result. So the set of values of a particular statistic, when you say statistic, means it is the mean or standard deviation, together with their relative frequencies constitute the sampling distribution. So when we take multiple samples from a population and we derive the information about that mean, then we get the sampling distribution of mean. That means we will have, let us say we have n samples, we get n mean values, and then those n means themselves have a distribution we call sampling distribution of mean. And this sampling distribution tends to approach a normal distribution if the normal number of samples is large. So see, the idea is to arrive at the information about the parameters from the statistics. And normal distribution, if you are able to achieve the normal distribution, then the sampling distribution gives the data about the parameters. So there can be sampling distribution of mean, sampling distribution of proportion. Proportion is like, fraction of the people having that particular attribute, proportion of the sample having that kind of attributes like success or failure, all different kind of attributes. We can have students T distribution, F distribution, chi-square distribution, and so on. So ultimately, our objective is to study the samples and deduce the parameters. Now, there is one important theorem, we'll discuss it here. So when we discuss this sampling distribution of mean, suppose we take n samples from a population and find out the means of those n samples. So what happens? You can see, if the probability distribution of all possible means of random samples of a given size are taken from a population, then what we get is the sampling distribution of mean. So the sampling distribution of mean follows, it tends to be a Gaussian distribution if the number of samples taken is large. That is what is called as the central limit theorem. What it says, the distribution of means of random samples taken from a population having mean, the population is having the mean mu and the variance sigma square. This distribution of means for a population having these parameters approaches normal distribution with mean mu and variance sigma squared by n as n tends to infinity. So you just take and focus on this one. What I have shown here, that suppose the original distribution here is Gaussian population distribution. Here it is a bimodal distribution, and here is a skewed distribution. But when you, so this is one sample. Take one sample and you do the measurements, you will get this statistics. But when you take more samples, so when you take 2 samples, 4 samples, 8 samples, 16 samples, and 32 samples, you see, you start, what you are studying is now the sampling distribution of mean. So the sampling distribution of mean tends to be Gaussian, irrespective of what is the original distribution. And this is what is called as the central limit theorem. So that means whatever be the original distribution of the population, if you take the means of the different samples, then the sampling distribution of mean tends to be Gaussian distribution with the mean same as population mean and the variance equal to sigma square by n, where n is the number of samples. So this central limit theorem permits us to use sample statistics to make inferences about the population parameters. So this is a very, very important theorem which helps us in deducing the population parameters from the sampling data. So there is a concept of standard error. The standard deviation of sampling distribution of a statistic is known as its a standard error. So from the sampling distribution, we get a mean, and the mean has got an error. That is called the standard error. So when we have the standard deviation of a population, we call sigma p, and the standard deviation from the samples we derived as sigma s. Then the standard error of mean x, where x is the mean, standard error of mean is given as standard deviation of population by root of n, when population standard deviation is known. So this sigma p is the population standard deviation. But many a times we don't know the population standard deviation. So we determine the sample standard deviation, and that divided by root n gives the standard error of mean. So the standard error enables us to specify the limits within which the parameters of population are expected to lie with a specific degree of confidence. So I discussed in the Gaussian distribution the degree of confidence depending upon the z value. So here you see, so x is the mean and mu is the true value for the population. X is for the sample, mu is for the population. So x minus mu, you can say, is the accuracy of the measurement. If it is less than 3 sigma x, then we can say within 99% or 99.7% that this is due to this belong to the same population. This mu, the x mu value within x within 99%, and if there is a difference, that difference is due to chance. So, and if x minus mu is more than or equal to 3 sigma, so you cannot account this difference by chance alone. That means it could be significantly different. So that is how we start conclusion about the outcome of a measurement from sample, whether this mean value is a part of population or not depends upon the difference between the mean, sample mean, and the true mean. So in this particular case, if x minus mu is more than 3 sigma, we say that difference is significant. That means this is not by chance, but it is really there is a difference. So x plus minus 3 sigma x is the normal curve, covers the area of 99.73%. So with this much percentage confidence, you can say in this case, this difference is due to chance only. Here, it cannot be accounted for by the chance. So this standard error, what we are telling, it gives an idea about the reliability and precision of the sample. So sometimes you may find that it will be a little confusing about when we say precision. Precision is the repeatability of a measurement. But you can see here, this is also derived from the standard deviation. So the standard deviation of mean the standard error of mean actually is sigma s by root n. So when you take large number of measurements, essentially you are improving the precision of your measurement and also the accuracy. You are becoming closer to the true value. Then there is another quantity called rather than sampling distribution of mean, we have sampling distribution of proportion, which is very useful in when we do a survey or when we are doing measurements of discrete numbers in any sample survey or different types of discrete variables we are handling. So we say sampling distribution of proportion. So proportion means fraction of items having a particular characteristics, like defective items in a set of samples. So suppose there is some company is doing some production of some item, and what fraction of this production is defective? They have some number. They do a sample analysis to tell like 99% of our samples are not defective, only 1%, or even it could be less. So any quality control exercise of a production unit will have these numbers. What is the number of percentage of proportion of defective items in your production, which you have to reject? It can also be stated in terms of proportion of successes and failures. Like, so it says success is P, failure is Q. So Q is equal to 1 minus P. So any times like coin, head proportion, the P for head, when you split the coin, P equal to half for head, P equal to half for tail. So P equal to half, Q equal to 1 minus half is half. To construct the confidence interval to estimate population proportion, binomial distribution is used, because here you are handling when you are calculating the proportion, you are seeing what fraction of the population is having this particular attribute. So you use the population binomial distribution. So you use the mean of binomial distribution is NP, where is the number of sample size, and P the probability, and standard deviation is now square root of variance. Sigma square was NPQ, standard deviation here root of NP. The mean of sampling distribution of proportion is taken as P with the standard deviation, also known as standard deviation error of proportion, root PQ by N. So we said that the standard error of proportion was sigma by root N in this distribution, sigma P by root N or sigma S by root N. Here we say sigma PQN square root by N. So that will become PQ by N. That is what is the standard deviation, and which we call as the standard error of proportion. So when we have a large sample size, the binomial distribution will become normal distribution, and the confidence interval for population proportion is given as P plus minus Z sigma. So sigma is PQ by N. So probability plus minus Z sigma is the confidence interval for a population proportion. So this we will utilize this in the when we are reducing the sample size in subsequent slides. Okay, now this is the sampling theory. So we have to suppose we want to deduce the mean or the size from the sample about the population. So that is what I discussed here in terms of the sampling theory. So sampling theory is used to infer about the attributes of a population from the statistics. What are the attributes? It could be defects of successes, or presence of an attribute, or absence of attribute, or yes, no, all sorts of, like election in a poll, opinion poll. Some people say this party, what is the probability of this party's candidate winning? So you say, would you give this vote to this party? Say yes. So become P equal to that one. Q is the 1 minus that. So the parameter value may be given, and it is only to be tested if an observed statistic is. So there are different aspects, different options. What kind of study you are looking for. So in one case, you have the parameter value, and you want to test it if an observed statistic is its estimate. So that means you are having the value of mu, and you are getting the X value. You want to know whether this X is an estimate of mu or not. That is the problem you have to solve. In other case, you are not given the mu value, but you want to derive it from the X value. So X is the sample mean and mu is the population mean. Another problem is examination of the reliability of the estimate. So X is the estimate, how reliable it is. So the problem of finding out how far the estimate is expected to deviate from the true value for the population. So X minus mu is the deviation, whether this deviation is significant or not, or this is by chance. That is what we discussed previously. We'll have more discussion on this subsequently. Like to test the significance of mean of a random sample, we use the t-test. So the t-test, t is equal to X minus mu upon sigma X. X is the sample mean, mu is the population mean upon the standard error of mean, where X is the mean, mu is population mean, and sigma X is the standard error of mean given by sigma X equal to sigma S by root n. If the population is not given, standard deviation not given, we take sample standard deviation divided by root n equal to the standard error of mean. Okay, so let us discuss in more detail that we want to compare the sample mean and population mean. If you are given the value of the population mean, you want to know whether this mean, sample mean and population mean belong to the same distribution or there is a significant difference. So I have given here the Gaussian with the confidence intervals. Like for 95% confidence interval, we can say mu plus minus 1.96 sigma, or in terms of Z, then it is plus Z value 1.96. So plus minus 1.96, it will be here minus 1.96. So this is the 95% confidence interval. And that's the area under the two tails is called alpha, and that is 5%. So that this area is alpha by 2 and this is alpha by 2. So if it is a 95% confidence interval, then this is alpha by 2 is 0.025, this is 0.025. So we use these values of alpha many times in calculation. So for 95% confidence level, alpha is equal to 0.05. So now if we have the known sigma, population standard deviation is known, then we can get what we call as the Z statistics. Z is the variate of the normal distribution, which we have derived here. And so Z is given as X minus mu by sigma by root n. So mu can be given as X plus minus Z sigma by root n, or so you can give one in terms of 1 minus alpha by 2. So sigma is population mean. So it is not sigma, it is mu. It is mu population mean and it is population standard deviation. X is the sample mean and mean of n samples, and S is the standard deviation of means. Now you can see here that if Z is less than 1.96, we are more than 95% confident that X is a true measure of mu. So that is what is the statement we are making based on the value of X and mu and the Z. So Z statistics means Z, the value of Z tells you about the confidence level. If you don't know the sigma of the population, then we measure the standard deviation of the sample. And so you can say now the confidence interval for mu in terms of the sample mean, mu plus minus t. So we call it not Z, but t. The t test, that is the t value, 1 minus alpha by 2, S by root n. That is called the student's t. So the t test for comparing the sample mean with the true or theoretical value is given by t equal to mu minus x upon S upon root n, where S is the sample standard deviation. So what essentially the t gives you? T is the ratio between how far the mean lies from the expected mean and the standard error of mean. S by root n is standard error of mean, and this is the deviation. So ratio of the deviation to the standard error is the t value. And so for a given value of alpha, that is the, it defines the confidence level, the degree of freedom observed t is compared with the tabulated value to conclude about x and mu. So this is what is the t-test we do. So I had just given you some of the data. This t-test is a big table. You can see it in the standard textbooks, even in the Google you will find. So the probability values for the two-tailed test means, when you say two-tailed means you have this two tails. Many times you don't have two tails because the negative values are not there. So for degrees of freedom of 4, 6, 10 and so on, these are the t values. So what you have to do, you calculate the t value, t equal to mu minus x upon sigma s, the standard error of mean. And for that many degrees of freedom, you find out the value of p and compare with the expected p. And then you can find out whether it is significant or not. Difference between the mu and x is significant or not. We will do these examples tomorrow. There is another test called F test, that is for comparing two sample variances. Let us say, suppose you are doing measurement by two methods and you get the two sets of data, A and B. So the objective is to determine whether method A should be replaced by method B, and you decide based on the variances. If variance of B is greater than variance of A, then it will not be replaced. So let the variances be SA square and SB square for the two methods, A and B. So the F statistics is given by SA squared by SB square, where for A we have m minus 1 degree of freedom, and for B we have n minus 1. So you have different degrees of freedom. You can compare F value. So compare the observed F value with the value in F table. And if the observed value is less, we can say A is better. So you can use this F statistics many a times, when you do inter-laboratory comparison, different laboratories have different samples and to the value. So you compare their standard deviation using the F test. Okay. The last aspect is the sample size distribution. So how much is the sample size to determine the population parameters? Now, this is a very important exercise because the sampling is an important exercise, and you have to optimize the sampling. So if you take too small a sample size, then may not serve to achieve the objectives. You may not get a true representative of the population. But if you take too large a sample size, then you may incur huge cost and you may waste resources because it may not be necessary to have too large samples. So that is why you have to optimize your efforts. So you save time, you save money, manpower by doing proper sampling. Now, when you want to decide the sample size, you have to take into account these following factors, like nature of universe. Suppose your population, the area which you want to survey is homogeneous. The sample size will do. Suppose you have a liquid sample you want to analyze, you have a big drum, homogeneous. So you don't have to take too many samples, small sample will do. But if you have a field sample rock, which is heterogeneous, maybe you have to take large sample. The number of classes proposed, many a times, you may have subgroups in the population or class groups, then you have to take a large samples. Similarly, the type of study that you are doing, if you are doing a very intense study or technical survey of type, a small sample may do. But if you are doing a general survey, where is a large number of parameters, then you may require a large sample. Similarly, the type of sampling, a small random sample is too much superior to a large but badly selected sample. So how good your sampling you are doing is also important. And finally, the standard of accuracy and acceptable confidence level. Depending upon what kind of confidence level and accuracy you are looking for, your sample size will change. For achieving high standard of accuracy, you use relatively large sample. And the typical scaling is that if you want to double the accuracy of fixed significant level, force significant level, then you have to increase sample size by 4-fold. So suppose you want to reduce the accuracy, I mean less difference between mean and the sample mean and the population mean, you have to increase the sample size by that factor. Okay. So let us discuss now the sample size when you estimate the mean. So suppose you want to estimate the mean, then what would be the sample size? This is the formulation. So if you have an infinite population, then the confidence interval for mu, so you have to actually get, you are measuring X, you are predicting about the mu. So mu will be X plus minus Z sigma P by root N, and you are, so if sigma P is the population standard deviation, so Z is the value of standard variate at a given confidence interval. N is the size of the sample, sigma P you know, population standard deviation, and you have to estimate it based on experience or some trial sample. So estimation of mu in a population with standard deviation sigma P. So suppose you are given that within this error, let us say 2% error between mu and sigma, mu and X, so that I am giving error is E. What should be the number of samples, sample size, if you are given the error? So that you can see here, actually this is the error. This is nothing but the error, because mu minus X is the error. So error equal to Z sigma by root N. So you want to find out how many samples you have to analyze, what is the sample size to get a estimate of mu with a certain error. So you can analyze this E square equal to Z square sigma square by N, or N equal to Z square sigma square by E square. So this is for a infinite population, because here you are taking the sigma P. But if you have a finite population, then you have to, there is a finite population multiplier. So the confidence interval for a finite population, mu equal to X plus minus Z sigma P by root N into a factor that is N is the population size minus small n sample size upon N minus 1. So this factor comes into picture if your population size is finite. So the error E is now Z sigma P by root N, N minus 1 square root. So you can transform this to E square equal to Z square sigma square by N into this factor. And so you can calculate from here, you can rearrange this in terms of small n. Small n will be Z square N capital N sigma square upon this factor, which I have written in terms of this. So sample size equal to Z square capital N sigma square upon N minus 1 E square plus Z square sigma square. So if you want to deduce the mean from the sample mean within a certain error, then you use this many number of sample size. That is how you can calculate the sample size. I have given an example here. So there are 5,000 cereal containers in a godown. How many containers do we have to weigh to determine the true weight of the containers, given the variance of the weight is 1 kg? This is on the basis of past record. And the estimate should be within 0.2 kg of the true average weight within 99% probability. So this is, this is how the problem is given. What is the problem given? N equal to 5,000, capital N equal to 5,000. Sigma, the standard deviation for population is 1 kg, you know from the previous history. Error is 0.2 kg. So for 99% confidence level, Z equal to 2.5. So confidence limit given by X plus minus Z sigma P by root N into this finite sample factor. Accordingly, you use this formula N equal to Z square and sigma square by this. So you can put the value here and get the value. This is equal to 1.159.98 means 160 is the sample size. How many containers need to be weighed if n equal to infinite? You can remove this term for sample multiplying factor. It becomes 165. So you see here, because your population is so big that the sample size does not make much difference. Instead of 160, you become 165. So this is how you can. So to predict the mean for 5,000 samples, you need to measure weigh only 160 samples. Other one is the sample size when estimating a percentage of proportion. This is encountered many times here. So proportions follow the binomial distribution. The confidence interval for population proportion. So this is the population. What is the fraction of population having a particular characteristics given by P plus minus Z root PQ by N. Root PQ by N is the standard error of proportion. And P is the sample proportion. P apostrophe P is this is the population proportion. So we want to get an estimate of P apostrophe from this P based on personal judgment or a pilot study. Then the given precision with the given precision rate, acceptable error can be expressed as E. So this is nothing but the E. So E equal to Z root of PQ by N. And you can again get E square equal to Z square PQ by N, or N equal to Z square PQ by E square, where P is the probability of success and Q is the probability of failure. You can also write Q as 1 minus P. So this formula gives the sample size in case of infinite population. And for a finite population, you introduce this term n minus 1, like in previous exercise. This is the formula for finite population. So here is that example again. So from a population of, let us say, 4,000 fuel pins, you have the fuel pins for a nuclear fuel complex preparing fuel pins for a reactor. How many fuel pins should be drawn to estimate the percentage of defective fuel pins within 2% of the true value with the 95% probability? So you cannot examine all 4,000 fuel pins, but you want to have that much confidence that with that confidence only 2%, within 2% you want to arrive at the number of defective pins. So n equal to 4,000, error is 0.02, z equal to 1.96 for 95% confidence, area under the normal curve. So now here you don't know the proportion of defectives in the universe. So from a pilot study, it can be taken as 0.02. And then you put the values of all the parameters in the formula for a finite size, Z square PQ n upon E square n minus 1 plus Z square PQ. You get 180 is the number of fuel pins you have to test. In case of infinite population, this 180 becomes 188. So, and if you want to have 99% confidence, Z equal to 2.57, then you have to examine 324 pins. So that is how you arrive at the sample size to deduce about the population parameters. So like this, what I gave you some typical examples, but it will be applicable in many, many cases. And like, for example, if you are doing an opinion poll, I just gave some examples where you can use this knowledge. How many voters have to be interviewed to predict the success of a candidate with 95% confidence? Assume only 2 candidates, a number of voters in constituency 1 lakh. So you can do a calculation. How many voters you must be seeing these days, these different channels are showing opinion poll, and they are having this exercise done to arrive at a particular voters, candidates winning chances. Similarly, you must have read in newspaper sero survey, or say this many percentage prevalence of sero survey, people have found antibodies against COVID-19. So when they are doing a survey, what they are doing, how many persons in like Mumbai city have to be tested for antibody against COVID-19 with 95% confidence. So you want to know how many people in Mumbai have got this antibodies. You cannot test everybody, but you should know how many people you have to examine for arriving at a meaningful result. Similarly, estimation of the number of diabetic patients in India. You must be hearing that in India, this many people are diabetic. This much percentage people in India are diabetic. So people have done sample survey for selected rural and urban population to reduce that numbers. Similarly, one of the problems I was seeing here, like doctors test about drugs, efficacy of drugs. A team of medical research experts feels confident that a new drug they have developed will cure about 80% of patients. They have done research. How large the sample size be for them to be 95% confident that the sample proportion of cure is within plus minus 2% of proportion, all cases that the drug will cure. So how many people they have to do the testing of with this drug to arrive at this number with 95% confidence? So these are the different types of problems one will be encountering, and this is where the statistics plays a very important role. So that's all I had to say today. Tomorrow we will discuss the other aspects of testing the hypothesis, reducing the precision and accuracy, errors in measurements, and so on. So if you have any questions, I can see. Yes. How it can be ensured that the distribution will be normal? And if it is not normal, how the results can be presented in terms of mean and sigma confidence level? So if it is a random, see, the most important part is that if you have the random sampling, then as I discussed, based on the central limit theory, for a random sampling, the data will fall on a Gaussian. But if it is not random sampling is not done, you may not see a Gaussian. And nowadays, of course, you are always having this in the computers, you can fit into a Gaussian, and you will see whether it is really fitting into a Gaussian or not. But to ensure that the distribution is normal, you have to do the sampling in a random fashion. Your samples are random, then based on central limit theorem, it will tend to a Gaussian distribution for a large value of n. Let me see any other question on the top. Okay, no questions on the top. Go down. Yes. So when we collect data for our experiment, we usually collect in triplicate or a set of 5. What statistical criteria do we use to determine if the number of replicates per data point is enough? Yes. So that is where I am telling that when you do triplicate measurements, you may not be getting the true representative of population. But then it may not be possible to do so many measurements. So that is why you have to normally you show multiple measurements, 5 measurements, or there is some quality control. So when you do the quality control, that means in your laboratory you take standard and do 20 measurements and to find out the reproduce the value of standard. So that is a part of quality control. You have separately done an exercise where you take a standard reference material, then you don't have to do it 3 or 5 times. You do 20 times to reduce the mu, the x value, you get the x value and find out how far the x is from the mu, because you know the mu value. And that is the kind of accuracy you quote in your measurements. So then when you do the actual experiment, you may be doing only 3 or 5 times. But before that, you have done a quality control check by taking 20 measurements in your standard reference material. in Z test versus T test, kindly clarify if N is sample size or number of samples. So N is the sample size. How many samples? Actually, you have taken to do a population, like, a population is like a mountain, let us say. And from that population, you want to derive information. For the population, you want to derive information about the parameters. So you have to take sample. Now sampling, suppose you take one sample from one, then you may not get the complete information. So you have n sample size. So that essentially sample size means what is the number of samples you are taking. So that is what is you have when you take n samples, you take n x values, and then you get the x bar for those samples. That is the standard sampling distribution of mean, and that sampling distribution of mean follows a Gaussian distribution, irrespective of whether the population distribution is Gaussian or not. So the central limit theorem is applicable when you have a large number of samples to be analyzed to predict about the population. Okay, so there are no more questions. We will stop here, and we will meet on Wednesday, second part of this lecture. Thank you. Okay, bye bye.